Good morning, everybody. I am Ari Caesar and presenting with Felipe Haro. Felipe, you can go to the next slide. I am the co-founder of Automation Intelligence. Company was founded in 2019, and we basically create software to optimize highly automated manufacturing, warehousing, logistics, and e-commerce processes. We're about 12 engineers based out of Atlanta, but spread out across the United States. Prior to this, my background is in operations research. I was working on a PhD in machine learning and mathematical optimization at Georgia Tech before starting this company. I'm presenting with Felipe Haro. Felipe.
Yeah, I'm Felipe. I'm the founder of Noorjax Consulting, which is a project I started in 2017. Right now, we are 6 people working in Noorjax. I have been doing simulations since early 2000s and started using AnyLogic in 2013, and I became an AnyLogic evangelist since then. So go ahead, Ari.
Awesome. Just for some context, here's some of the companies that Automation Intelligence works with. Not much to say here other than, we have tremendous experience solving very large problems for the largest companies. So the bigger, the better. Awesome. So we can advance. So what am I going to be talking to you about today? Like the title of the presentation suggested, we're going to be talking about TiltTray sortation. So what is a TiltTray sorter? Basically, a TiltTray sorter is a high-speed sortation device that sorts small and medium-sized parcels. And the way that it works, you can see that parcels get inducted onto trays. Parcels can take up, multiple trays in some systems, depending on how long they are. And when the parcels reach the destination that they're going to, as you're about to see on the left, the tray tilts and the parcel gets ejected. And so these have some uses in things that you would be familiar with, baggage handling. So when you check a bag, that bag needs to get sent to the correct gate, and that's using a TiltTray sorter. Similarly in parcel sorting, so when you send a small package through UPS, those packages get diverted to a separate area of the facility and get grouped based off their destination. So they get put into bags like you'll see here on the right. And then those bags carry on to the final destination so that all those small parcels don't have to get sorted at each and every hub down the line. Similarly, in distribution centers, as orders are coming in, folks are picking those orders in bulk, and then TiltTray sorters are grouping them based off of where they need to go, either for store or individual order. Next slide. So just a few other facts to motivate this discussion. So in practice, TiltTray sorters typically have multiple induction areas. So as you can see on the left, there are multiple induction lanes that are feeding the trays. That's important. That's the key here. That means that we have a decision to make. We can decide which lane feeds each tray. Today's systems are typically built using first in, first out logic. And as I'll show later in the presentation, that is suboptimal. Additionally, the trays can have different lengths. In the examples you see here, they're the same length, but they can have different lengths. Additionally, discharges can't happen back to back. So as you see here on the right, as parcels are being discharged, after one parcel is discharged, we need time for that lane to reset. So somebody's got to pull a suitcase out. So depending on the speed of the conveyor and the size of the object, that can be anywhere from 1 to 4 trays that need to pass between successive discharges to that same lane. And that's important because anytime you have 2 parcels that are going back to the same destination, those parcels will recirculate and block new parcels from entering the system. All right, next slide. So like the title of the presentation suggested, there is opportunity here to improve the performance of these systems. And what we found through our work here is that this first in, first out logic causes a 10% decrease in total throughput. And that's pretty major when you think about distribution centers or parcel sorting facilities like UPS during the holiday season is turning away packages. And distribution centers for major retailers are completely overrun during the holidays. So with a 10% increase in throughput, for every 10 facilities you needed before, now you only need 9. And when you consider that these buildings cost hundreds of millions of dollars, this is a very major opportunity. So let's talk about why the current logic is inefficient and suboptimal. So there's basically 2 components to this. And the first is that the first in, first out logic, when you have trays that are different sizes, does not consider the size of the parcels relative to the size of the trays, right? So what I've done here is I've shown on the left an example where we've got 3 small parcels and 1 larger parcel. And on the right, you can see that you've got a pattern where you have trays that are 2 small trays, 2 big trays. And this is, this is not a made up example. These tray dimensions are from a real distribution center. And so you can see that if the red parcel arrives first, the greedy algorithm is going to put that on 2 smaller trays, right? Then it's going to put the yellow parcel and then the blue one. Whereas if we were taking into consideration the size of the parcels and the size of the trays, we would realize that it makes sense to put that red parcel on a larger tray, wait to assign it, and then we can get 4 parcels on here instead of 3. And so this is an example of how the greedy first in, first out assignment is suboptimal when you have trays of different lengths. But the real opportunity here is on the next slide, has to do with recirculation. And so just like I mentioned earlier, generally these systems need multiple trays to pass before you can allow another parcel to be discharged to the same lane. And so this second yellow parcel here, if we're using first in, first out assignment and we place this second parcel going to the same destination after this first one, this second parcel is going to recirculate, which means that it's going to block a new parcel from entering the system and going to jam the system up. So we basically are creating a bottleneck that shouldn't exist. And so by making smarter decisions and using the other induction lanes to put packages on these 3 trays and waiting to put this parcel on the following tray, we can avoid that recirculation and get parcels out of the system sooner and free up more trays. So how did we go about trying to solve this? Well, we used a technique called mathematical optimization, also known as mixed integer linear programming or mathematical programming. And the way that it works is it translates a business or a decision problem into a math problem. It's got 3 components. You've got decision variables, you've got constraints, and you've got an objective. The constraints and objectives are typically linear functions of the decision variables. The one good thing about mathematical optimization, or there's many good things, I suppose, but one of the really good things about it is it comes with a guarantee. So if our objective is to maximize throughput, we can guarantee that no other methodology will come up with a solution that has a better throughput than what this mathematical model came up with. And that's very powerful. The problems can get very large and take a long time to solve. And I'll show some examples on the next slide. But fortunately, there are solvers and high-powered computing that can get results rather fast. So just to dive a little bit deeper and kind of provide some context on what I mean. So like I mentioned, a mathematical model has 3 components: decisions, an objective, and constraints. I'm not showing the equations for everything. They get a little bit dense, but just so you can see, our decision here really is whether or not for every parcel and for every tray, we want to know whether or not that particular parcel should go to that particular tray. So if we have an example with 20 parcels and 50 trays, we've got to make 1,000 decisions to tell us which parcels should be on which trays. And our objective is to maximize throughput. We want to get as many parcels into this system as possible. And then when you create a mathematical model, you have to tell the system how these variables are related and what the constraints are. It doesn't know that, right? So, for example, we can't have more than one parcel per tray. So this would be an example of, you could say, okay, for this decision variable X, for every single value of T, when we sum over all the parcels for that particular tray, we can't have more than one assigned, right? Similarly, if a parcel is longer than a tray, it needs to use the following tray as well. So we need to enforce those relationships. Parcels can't jump over each other. We need to have a certain amount of time between parcels being discharged, and then we actually, prevent the recirculation from happening based off of the way that we assign the parcels. But the mathematical optimization is only one component, right? That solves a particular instance with parcels and trays. Now we need, a full-scale solution to be able to test this. So how did we go about architecting this solution? We can advance Felipe to the next slide. So working with Felipe, we came up with an example of TiltTray sorter. The left and the right side that have the 4 lanes, those are the induction lanes. And then the top and the bottom with the 10 lanes, those are the output or discharge lanes. Felipe will go into all the wonderful things that he did to make this completely customizable. So this is, one example, but basically AnyLogic is going and creating the parcel arrivals, and it's sending information to our solver using Gurobi and Python. And so we've got here, different information about where the parcels are, what lane they came from, where they need to go to, etc. We've got information about the trays, whether or not they're occupied. We use a REST API to query the solver, and that's really important because ultimately, we want this to be a product that works in real life. So whether it's AnyLogic or whether it's a real TiltTray sorter that needs to know, hey, I've got these parcels in these trays, what should I do? Our solver is agnostic. It receives a REST API call, and it on the next slide, you can see returns back the assignments of which parcels should go to which trays. So I'll turn it over to Felipe to talk about how we did the simulation.
Okay, thank you, Eric. So in a way, in this presentation, and this is one of the reasons why I find this project interesting to show in a conference, is that we have a few things at different levels of complexity that are useful for all AnyLogic users that are looking at this conference beyond the results that we get from this particular business case. So there are 3 things that I want to talk about. One of them is the ability to make a system as flexible as we want. So Ben Schumann already talked about this during this workshop this morning, and it's to use a data object input that allows you to parameterize everything in the simulation to be able to modify its physical and operational parameters. The second thing is making functionalities as customized as we want. So AnyLogic provides with a set of blocks for discrete event models that allow you to do a lot of things in a very flexible way. But the functionalities are limited to a certain degree. And AnyLogic provides flexibility to solve its flexibility problems in a way. So you can do an agent-based model, use agent-based and system dynamics to do discrete event models. So you use agent-based for the functionality, system dynamics for the physical dynamics of the system. So, and also the third point is to communicate agnostically with other systems. This is something that comes on Stack Overflow pretty often, how I communicate AnyLogic with something else. And we investigated the UDP, which is the datagram protocol for communication, and REST API that uses TCP/IP. And for the communication language, JSON is the perfect way to do this, because the server or the receiver that doesn't care if it's AnyLogic sending or something else. And the same way AnyLogic is sending, and AnyLogic doesn't care who is receiving it. So we're pretty agnostic in that sense. So let's talk about the different options. So in terms of flexibility, you have the system that can be applied to any sorter in existence. So any conveyor, circular conveyor in existence, as long as it follows a set of parameters. So in this sense, we have this data object that has all the elements that you need in order to build this conveyor in any way you want. So some of the parameters are the oval length, the oval width, the radius curve, the number of input lanes, the number of output lanes, the size of outputs and input lanes, among other things. So you have this table, for example, when parcels or packages come into the system through the input lane, you can define what is the probability for each size for a particular parcel. And you can use a custom distribution in AnyLogic to be able to accommodate for that. So this becomes a pretty flexible project, pretty flexible conveyor. So we can see two examples here. So on the example on the left, you have, this is all done programmatically, so nothing is built with any conveyor done by AnyLogic. Everything is done programmatically, so you can create two input lanes for output lanes and kind of a circular conveyor that is able to do the same thing, but it accommodates for any layout that you have in your particular system. On the second one, on the right, you have a much bigger central conveyor that is, in this case, 200 meters length, 50 meters width, and you have 4 input lanes and you have 6 output lanes. So this system is much bigger than the one on the left. So in a way, you can construct programmatically based on your data object any shape for this conveyor that you want. So you can apply it for any industry and you don't need to make a new model again. So the second point is customization. So if you see this conveyor here, you see that all the trays are of the same size. We saw this on the videos that Ari showed you as well. And this is pretty similar to the kind of conveyor that comes with the AnyLogic machine handling library that allows you to put one object in one cell. This is pretty standard, but in here we have a bit of an option to put one object in 2 trays at the same time, which is not necessarily possible with the AnyLogic library. But we can go even further and create different sizes, because some facilities have this configuration and we need to accommodate for that. So in this case in particular, we have a pattern of 2 small trays followed by 2 bigger trays that can accommodate objects in any way that is needed based on the optimization. And here again, you can have one object that is using 2 trays of different size. So we have a completely flexible system that can be used in any facility. And this is one of the reasons you want to use AnyLogic for this kind of project. So the third thing is about communication. And this is the typical question, like how do you communicate with even Python if you don't use the pipeline, which is the library done by AnyLogic to communicate with Python, but you can do something else. So the first option that we tried is the UDP protocol. So the UDP protocol, you send information to a server, and this information is created in JSON. JSON is pretty good because it's very easy to read from a human, and it's also easy to read for a machine. And there are a lot of libraries in Java that allow you to do this pretty seamlessly. Now, the issue with UDP is that even though it's faster than TCP/IP, for example, in terms of communication with the server, it is less reliable. So in this case, you need to pause the simulation and wait and create a thread in AnyLogic in order to be able to wait for the receiving message, which is not always guaranteed. But if you get it, then you have a tray assignment and you are ready to go. But even though UDP is great, we found a better way to do this through the REST API, which is TCP/IP as a protocol, and this ensures that you will get a response from the server. So the same way you have a tray assignment request, you want to know where to put the parcels in which trays, and you create an HTTP request using JSON as the body, and you use the post method that comes with this request because you want to put the JSON message in the body of what you're sending. So you see down here that you can use directly a URL, which has some parameters that you can define in the URL, and the rest is information that comes in JSON format. So when you generate the HTTP request, you don't need to pause a simulation because the response from the server is guaranteed. And when you get the response, you get the tray assignment, and then you have an optimized way in which to put parcels in a tray. And this is of course, TCP/IP is a bit slower, but it's completely reliable. And okay, Ari, so you will talk about results now.
Yeah, absolutely. So one of the things, so for the results, I thought it would be interesting to kind of show what happens when the system is not exactly at capacity, right? And so here you can see for the optimized algorithm, we consistently have a lower tray utilization. So what is tray utilization? That's the number of trays that are full at any given time, the percent of trays that are full. And so intuitively, this makes sense, right? When the optimized algorithm is minimizing recirculation, that means that those parcels are getting to their destinations on the first go around, and they're getting discharged. And so for both of these experiments, in this particular example, it's the exact same stream of parcel arrivals. So we configure the random seed to be exactly the same. The only difference is the algorithm that is assigning the parcels to the trays. And so you can imagine what happens then as you start to push this the parcel arrival rate higher. The naive method, the first in, first out, is going to hit the ceiling, right? There are going to be too many recirculating parcels that are taking up more trays, and it's not going to leave enough room for additional parcels to enter the system. And so as we start to push this up, what happens is the naive method freezes, whereas the optimized method has additional capacity to take on more parcels. And that's really where that 10% increase, that benefit comes from, is by building out additional capacity, by minimizing recirculation to absorb more parcels.
Okay, awesome. Yeah, so there are a few questions. Should
Cool.
I read them?
Yeah, let me see here. So we've got what solver do we use? We use Gurobi. I had looked initially at Python has there's a Python package called Python MIP. And when I switched to Gurobi, the solve time increased by over 100x. And that's really important, right? Especially when, in AnyLogic, we speed up the simulation. If we had to wait, seconds or I don't think it would take a minute, but if you're waiting seconds for every API call, you're dead in the water. So with Gurobi, the solve time is in milliseconds, like several milliseconds. So actually, yeah, that was one of the next questions here is what is the solve time?
Now, question: how do you calculate the probability of the size of the parcels? So, as I showed you on the table as Excel, you have sizes and the probability. This is defined. This is a user-defined parameter that you can change depending on the situation of your system. So, as I said, this is pretty flexible. And from the AnyLogic perspective, you just need to use a custom distribution, which is a good choice in order to define this, because you have the probability, kind of the frequency, and the values. So, yeah, if you don't know the custom distribution, help documentation.
Yeah, that the parcel size distribution and the tray lengths in this example were actually taken from an example from one of the largest retailers in the world. They came to us and said, "Hey, we're not getting as much out of our system as we'd like," and so these are the shape of the TiltTray I changed, for this example, but the tray sizes and the parcel sizes are the same. And earlier, Felipe, somebody had asked the probability distribution. I don't know if maybe they were talking about for parcel arrivals, but perhaps you want to address the Poisson.
No, yeah. So you have a Poisson distribution, but this is not. I don't know what the question is really.
I think they were asking determine probability. I don't know if he was asking about the arrival rate, but yeah, we used Poisson to model parcel arrivals. Somebody asked, does the AnyLogic and Gurobi run simultaneously? So yes. So every time we see new parcels arriving, that triggers an API call to a server that's running our solver with Python and Gurobi. That's a REST API call that it receives, and it returns back again with JSON the assignments. So these things are running in tandem, and like Felipe mentioned earlier, AnyLogic doesn't care where it's sending the request to. It's sending it to a certain IP address and a port, but it doesn't care whether it's Python or whatever it is that provides the answer. And similarly, the solver is like a black box. Anything could ask it a question, and it will return back a solution to that IP address.
So yeah, this comes with it's the same question, like why didn't we use pipeline? Pipeline, for the ones who don't know, is like an interface that allows you to use Python inside AnyLogic, but we use pipeline because even though there's a Python script on the other side, we want to make AnyLogic completely agnostic to whatever system is on the other side. So if you use pipeline, you're forced to use Python, but if you use this REST API or even using UDP protocol, you can just send to anything, and to an IP address with a certain port, and it doesn't matter who receives it. And it's much more. We want to be agnostic, basically.
Let me see if I can't bang out these last two questions here that I see. The first one is at UPS, the data is captured when a label is created, but that would mean you have an API that is integrated to their database and are able to compute the right tray to use. Yeah, so in practice, when this gets deployed, in a particular facility, they have that information, and the way that we design the API to be used, that gets passed along in the API call. The last question is, what happens if you eventually get a bad solution with a huge MIP gap, and also can the model return infeasible? We don't specify a MIP gap here because we can solve this model to optimality in milliseconds. And so in terms of returning infeasible, infeasible only happens if there are not enough parcels and not enough trays for the parcels, but we have mechanisms for handling that. So no infeasibility, and we solve to optimality in milliseconds. Thank you guys for all the questions. That was great.
Yeah, thank you.
Thank you very much, Felipe and Ari. And I also would like to remind that Noorjax Consulting is also our sponsor today. So please feel free to reach the sponsor booth, schedule a call, and learn more about our sponsors.